All right, so let's start then. So we were talking about Riemannian manifolds, and as an example of Riemannian manifolds, we looked at submanifolds of Rn, right? So these were Riemannian manifolds with the induced Riemannian metric. So let me draw you a picture. So submanifolds of Rn. These are Riemannian manifolds with the induced metric from Rn. So this means the following. You have your submanifold. So suppose, for example, S2 inside R3. And at any point of the submanifold, the tangent space at that point is naturally identified with a subspace of Rn and the identification is via the derivative of the inclusion map. So this is 1-to-1 we saw last time. Okay, so here I is the inclusion map from the submanifold into Rn. So this is a smooth map, and its derivative gives an injective linear map from the tangent space to Rn. So this is TPM is identified with the subspace of Rn. So you can restrict the Euclidean inner product on Rn to the tangent space TPM. And this we saw defines a smooth Riemannian metric on M. And so once you have a Riemannian metric, you can measure lengths of curves. And once you can measure lengths of curves, it's natural to ask what are the shortest length curves between 2 points, say P and Q. And we got a necessary condition for a curve to be a shortest length curve by considering, so you take, so say gamma is a C2 shortest length curve from P to Q in M. Then we can consider variations of this curve by other curves, gamma T joining P to Q. So given what's called a vector field along gamma, so what is a vector field along a curve? This is a map. So suppose gamma goes from an interval AB into M, then a vector field along gamma is a map defined on the same interval AB, mapping into the tangent bundle of M, Tm, such that for each t, the vector tangent vector Vt is a tangent vector based at the point gamma t. So Vt belongs to T gamma Tm for all t in AB. Okay. So how do you get such a vector field along gamma? So example, if you take a one parameter, a smooth one parameter family of curves, say gamma S for mod S less than epsilon, okay, all defined on the interval AB, then you get a vector field along gamma Vt equal to del del S at S equal to 0 of gamma S of t. Okay, so this is a tangent vector at gamma t. Is this clear?
Yes, sir.
And if we assume that the gamma S's have the same endpoints, okay, so with fixed endpoints, PQ, then when you differentiate at t equal to A and at t equal to B, this is constant as a function of S, so the derivative is 0. So then you get vector fields along gamma which vanish at A and B, right? All right. Yes. Okay.
Yes.
So what I won't prove, but the converse is also true in a sense that if I start with a vector field along gamma, which vanishes at the endpoints A and B, then you can construct a C infinity one parameter family of curves defined for S small with fixed endpoints P and Q, whose variation vector field is equal to V. Okay, so you can go backwards in this correspondence. Is the statement clear?
Yes.
So for any variation vector field, you can obtain it as the variation vector field of a family of curves. All right, so the vector field vanishes at P, and then maybe it slowly increases like this, and then again it vanishes at Q. Okay, so you can sort of get a family of curves like this. All right, so that when you differentiate with respect to the parameter S, you get back the vector field V. Okay, and then what we said was that if I look at the lengths of these curves gamma S, then because gamma is the shortest length curve, for S equal to 0, so here gamma 0 is equal to gamma, in this family. So for s equal to 0, this function of s attains its minimum. So that means that DDS of the length of gamma s at s equal to 0, this is equal to 0, right? And so using this, that the derivative of the length vanishes at s equal to 0, we got the following equality, that the integral a to b of Vt gamma double prime t tangential component dt, this is equal to 0. And this is true for all variational vector fields V along gamma. So I'll write the space of vector fields along gamma as chi of gamma. Okay, this is a vector space. This is the space of vector fields along gamma such that they vanish at the endpoints, right? So VA equal to 0 and VB equal to 0. Okay. So we got this by computing the derivative of the length, assuming that gamma was unit speed. We could differentiate the length at s equal to 0, and you get that it's 1 over some constant c times an integral v prime t gamma prime t. And then here we did an integration by parts, basically. Okay, you do an integration by parts, you write this as a derivative minus another term, then you integrate the derivative by the fundamental theorem of calculus. So you get some boundary term, v inner product gamma prime evaluated at b and a. And this boundary term vanishes because we're assuming that v vanishes at 0 at a and b. Okay, so the boundary term vanishes. So you just get an integral of v inner product gamma double prime. And then you use the fact that v is tangent to m. So the inner product with gamma double prime is the same as the inner product with the tangential component of gamma double prime, right? Because the inner product with the normal component is 0. So only the inner product with the tangential component occurs. And so we get this equality. Is this clear?
Yes.
Okay, so this is a standard technique in the calculus of variations, right? You might have studied calculus of variations in some earlier course, right? This equation, so this technique of differentiating the functional and then integrating by parts, you end up with what's called the Euler-Lagrange equation, right, for the functional. You've heard of the Euler-Lagrange equation, right? So
Yes.
in calculus of variations. So here we get that this integral v gamma double prime tangential component is 0. Since this is true for all variation vector fields which vanish at a and b, this implies that gamma double prime tangential component is identically 0. Is this okay?
Yes.
Right? Okay, the point is this is true for all v, and therefore gamma double prime tangential component is 0. So this equation, this last equation, this is the Euler-Lagrange equation for the length function. Is it clear?
Yes.
Okay. So this gives us what's called the geodesic equation for the manifold, the submanifold M. Okay, so this is saying that the acceleration, this gamma double prime is the acceleration of gamma, right? The acceleration in the tangential direction is 0. The only acceleration is in the normal direction. Okay. So any length minimizing curve it can only accelerate in the normal direction. So to give you a concrete example, in this sphere S2 in R3, you probably know what these shortest length curves are. So for example, from the North Pole to the South Pole, the shortest length curves are longitudes, right? Okay. Now, longitudes are examples of great circles. So what are great circles? Those are the circles given by the intersection of the sphere with a plane passing through the origin, a two-dimensional plane passing through the origin, like this. All right. Okay. So here we'll take basically all planes passing through the North and South Pole. So those will contain the origin also, right? And the intersection will be longitudes. Is this clear? So the intersection will be a circle in this plane also, right? The intersection will be a circle in this plane. Yes?
Yes.
Yes, sir.
Now, here we can verify explicitly that the acceleration is normal to the manifold. So here at a point here, what is the normal direction to the manifold? Is just the radial direction, right? Right, the normal vector is equal to the radius vector. Let me call it P itself. Okay, if this is a point P on the sphere, right, the normal vector is equal to the radius vector. Yes?
Yes.
Now, in this plane, if I choose coordinates, XY coordinates on this plane, then my curve, this longitude, so let me call this, say, gamma. Gamma of t will look like what? With respect to these coordinates, it will be cos t sine t, right? Okay. Yes?
Yes.
Yes.
It's just a circle in a plane. So I'm choosing orthogonal coordinates, orthonormal coordinates in this. That means I choose an orthonormal basis of this plane. And then with respect to that orthonormal basis, I get X and Y coordinates, right? So I can write gamma with respect to those coordinates as cos t sine t. So then what will gamma double prime be? Gamma double prime will be just minus cos t minus sine t, right? Yes. If I
Yes.
differentiate this, so
Yes.
this is minus gamma t, right? This is minus gamma t. So this is minus the normal vector, right? Is it clear?
Yes, sir.
So you can see that in this picture, you see the tangent vector looks like this. If I move a bit, then what happens to the tangent vector? It looks like this. The change in the tangent vector is the acceleration vector. The acceleration vector is pointing towards the origin. Okay, can you see the picture? Yeah.
Yes.
Okay, in physics, it's what you call centripetal force, right? When you move in a circle, the acceleration points towards the center, right? So you can see that. So, so this tells me that this at least satisfies the geodesic equation, right? That the tangential component of the acceleration is 0. Okay.
Yes.
Okay. Fine. So we know how to now look for shortest length curves in a submanifold of Rn. You look for curves whose tangential component of acceleration is 0. So here, notice what we're doing here. We're looking at DDT of gamma double prime is what? It's DDT of the tangent vector gamma prime, right? So gamma prime gives me a vector field along gamma, right? Okay. Gamma prime is a vector field along gamma, and I'm differentiating. It's taking values in Rn, therefore I can differentiate it. And then I'm taking its tangential component, right? And I'm setting this equal to 0. So now this gamma prime, you see, it takes values in different tangent spaces, right? But we're getting a derivative of gamma prime, which is valued in the tangent space to the manifold, right? By taking the tangential component, right? So this suggests a way to differentiate vector fields along gamma. So if V is a vector field along gamma, right? So then V is a map from the interval AB to the tangent bundle of M. So this you can identify with a subspace of M cross Rn, right? Because all of the tangent spaces are identified with the subspaces of Rn. Okay, so this tangent bundle I can identify as a subspace of this product. Is this clear? Right?
Yes.
And so my vector field, if I look at its second component, that takes values in Rn, right? So, so that I can differentiate, right? Okay. So then I get a map from vector fields along gamma to vector fields along gamma, which I will call capital dV dt. This is defined to be, so what I do is I differentiate, I take the usual derivative of gamma, that takes, so of V, sorry. I take the usual derivative of V, that's taking values in Rn. So I can differentiate it as a curve in Rn. I get a vector in Rn, and then I take its tangential component. All right. So this will again be a vector field along gamma. Yeah, this is valued in the tangent space to the manifold. Is this clear?
Yes, sir.
Okay.
Yes. And this vector field along gamma, dV dt, this is called the covariant derivative of V along gamma. Okay, sorry, I'm getting some phone call. I'll just take it 1 second. Sorry. Sorry, just 1 second. One second, sorry. What happened was my cursor. Okay, that's it. Yeah. Okay, 1 second. Okay, sorry, yeah. So some problem with my internet, so I was just talking to them. Okay, so is this clear? You can define a covariant derivative of a vector field along a curve in this way.
Yes.
And this also suggests how to define the covariant derivative of a vector field on the manifold, not just a vector field along a curve, right? So let's come to that. Oh, so yeah, so in terms of this, the geodesic equation is what? The geodesic equation is the following equation, that the covariant derivative, capital D dt, of gamma prime is equal to 0, right? This is the geodesic equation. Okay. All right. So now let's come to the covariant derivative of vector fields on M. Okay. So we do something similar to what we did for vector field along a curve. So suppose X is a vector field on M. So X is a map from M to Tm, which again we are identifying with a subspace of Rn cross Rn, right? So M is mapping into Rn, and also Tm, I mean, all the tangent spaces Tpm are mapping into Rn. So I can identify it with a subspace of Rn cross Rn. So if I consider only the second component, which is a vector taking values in Rn, then I can view my vector field as a map, a smooth map from my submanifold M in Rn to Rn, right? It's a map from the manifold into Rn, okay? Such that X of P belongs to the tangent space Tpm, which is a subspace of Rn, all right? This is true for all P. And so since it's a map from a manifold into Rn, a smooth map, I can look at its derivative, dxp. So this is going to be what? A linear map from the tangent space Tpm into Rn, right? Yes? Okay. Is that clear?
Yes, sir.
So now I can define, given a vector v in Tpm, I can define the covariant derivative of x in the direction of the vector v as follows. So our notation for this is nabla sub v of x. This is defined to be the derivative dxp applied to the vector v. Okay, so that takes values in Rn, and then you take its tangential component. So that gives you a vector in Tpm. Is this clear? Okay. Right. So, you have your vector field on the manifold. Okay. So the vector field is tangent to the manifold everywhere. And what we're doing is basically, if this is a point P, and this is a vector, say V at P, okay, then what will dxp of V be? I can write this as ddt at t equal to 0 of x of gamma t, where gamma is a curve such that gamma 0 is P and gamma prime 0 is V. Okay, so this x of gamma t, this is taking values in different tangent spaces for different values of t, but all the tangent spaces are subspaces of Rn. So all of these values x of gamma t are vectors in Rn. Therefore, I can differentiate this, right, as a curve in Rn. Is this clear? So when I differentiate, I'll get a vector in Rn. Yeah, so for example, here, I take a curve tangent to V, and I look at my vector field along this curve, restricted to this curve, and then I differentiate it at t equal to 0. So I get a vector in Rn, then I take its tangential component. Okay. So this will be the covariant derivative, nabla sub v of x. Is this clear?
Yes, sir.
So this will be again tangent to, this will be a vector in TPM. Okay. And so now once you have the covariant derivative of a vector field with respect to a tangent vector, then we can also define the covariant derivative of a vector field with respect to another vector field y. So if y is another vector field on M, you define nabla sub y of x. This will be again a vector field on M. What is its value at a point P? So nabla sub y of x at P is simply nabla sub y of P applied to x. All right, so that means at the point P, you take the vector y of P and take the covariant derivative of x in the direction of the vector yp. Is this clear?
Yes, sir.
Okay, so this will give you a vector field on M. All right, this will give you another vector field on M. Okay, so in this way, from a pair of vector fields x, y, we've got a new vector field, nabla sub yx. Okay, so therefore we've got a map nabla from chi-m cross chi-m to chi-m, right? Any two pairs, any pair of vector fields is going to give a third vector field. Yes. So we have this map nabla from chi-m cross chi-m to chi-m. And so this satisfies the following properties, that with respect to the vector, I mean, with respect to which I'm differentiating, the vector v here, the vector field with respect to which I'm differentiating, nabla is linear in the first argument, and it's in fact C infinity linear. Okay, so if I take a linear combination of two vector fields x and y with coefficients which are functions f and g, okay, then nabla in the first variable is linear with respect to linear combinations with coefficients which are functions. So it's linear as a module map, all right, as a map of modules, where the space of vector fields, this is a module over the ring of functions C infinity M, right? Okay. So is this clear?
Yes, sir.
Okay. Now in the second variable, we have to be a bit careful. It's linear with respect to constants, with respect to scalars. So if I take scalar linear combinations of two vector fields y and z, then it's linear. Okay, so here alpha and beta are scalars. So it's R linear. Okay, it's linear over the real numbers, but it's not linear in the second variable over the functions. If I take nabla x of a function f times y, then we have this Leibniz rule. This is equal to f times nabla x of y plus the vector field x acting on the function f into y. Okay. So this is a Leibniz rule, right? In the first term, we're differentiating y and with respect to x and keeping f fixed. In the second term, we're differentiating f with respect to x and keeping y fixed. Is it clear? This is a Leibniz rule. Yeah.
Yes.
So why is this? So 1 and 2 are easy to see, properties 1 and 2. So let me just say why 3 is true. So for 3, you note that by the usual product rule, if I look at D of the map f times y, this is going to be df at p into y plus f of p into dy at p. Yes, is this okay?
Yes.
Right. So now what is nabla x of fy at P? This is going to be by definition d of fy at P applied to xp, and then you take the tangential component, right? Okay. Now this becomes therefore df at P applied to xp into yp tangential component plus fp into dyp of xp tangential component, right? Using the above equation here. Okay. Just 1 second, let me. Yeah, this hand is a better cursor, it's easier to see. Okay, so is this all right? And then from this equation, yp tangential component is just yp itself because y is tangent to m. And this dyp of xp tangential component, this by definition is nabla xy at P, right? So we get that nabla x of fy at P is xfp. Oh yeah, this dfp applied to xp by definition is xf at the point P, right?
Yes.
Yes.
Okay, so we get this this property 3 holds, this Leibniz rule for the map nabla. Okay, so now we make a definition for a smooth manifold M, a map nabla from vector fields, cross vector fields to vector fields, which satisfies axioms 1, 2, and 3, is called a connection on M, or an affine connection, sometimes it's called. Okay, so so a connection is C infinity n linear in the first variable, it is R linear in the second variable, and it satisfies the Leibniz rule in the second variable. Okay, so these 3 properties are the axioms for a connection on a manifold. Is it clear?
Yes.
Okay, so we have a connection on a submanifold of Rn, right? We've defined nabla when M is a submanifold of Rn, right? So this is called the induced connection on M. Okay, this is called the induced connection on M. So there's less than a minute, so let me stop now and we'll start again. Okay. 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 So this induced connection on our submanifold of Rn, which is a Riemannian manifold, it satisfies 2 very important properties. So this induced connection nabla on M satisfies, the first property is called symmetry, that nabla xy minus nabla yx is equal to the bracket of x and y. Okay, so this is the first property. This is called symmetry of the connection. And the second property is called metric compatibility, that this is again a Leibniz type rule, that if I apply a vector field x to the inner product of 2 vector fields y and z on M, then this is equal to the inner product of nabla xy with z plus inner product of y with nabla x of z. Okay, so it's a Leibniz type rule. First you differentiate y with respect to x, take the inner product with z, and then you differentiate z with respect to x, take the inner product with y. Okay. So let's see the proofs of these 2 properties. So for symmetry, so given 2 vector fields x and y on M and a point P in M, okay, so let phi t be the local flow of x, all right? So this is defined on a neighborhood U of P and M, okay? And these phi t's, these are maps from U into So these are maps from U in M into M, and M is sitting inside Rn. So I can think of these as taking values in Rn. All right. These phi t's are maps from a subset of M into Rn. Okay. And so the local flow allows us to define a map on the product phi from the interval minus epsilon epsilon cross the open set U into Rn, where it's just phi of t comma q is phi sub t of q. All right. So this is for mod t less than epsilon and q in U. So this map is smooth. Okay. And now we want to work out what this map looks like, capital phi. So look at phi of t comma q. So we can use the fundamental theorem of calculus in the t variable and write this as phi of 0 comma q plus the integral from 0 to t of del phi del t at s comma q ds, right? This is just the fundamental theorem of calculus in one variable. Okay. Is this all right? Yes?
Yes.
Now I make a change of variable to make this integral from 0 to t. I make it an integral from 0 to 1. Okay, so what do I have to do? I have to make put a new variable u equal to s over t, or s equal to tu. Okay, so with then the variable u goes from 0 to 1, and so my ds becomes t du. So I get a factor t coming out. Okay, and then this becomes integral 0 to 1 del phi del t of tu comma q du. Now this term inside del phi del t of tu comma q, this I write again using the fundamental theorem of calculus as del phi del t of 0 comma q plus an integral from 0 to tu, okay, of del squared phi del t squared of well, another variable. Okay. And then I make a change of variable. So that the final, what I get inside is going to become tuv, and outside I'll have tu. And I get an integral 0 to 1 del squared phi del t squared of tuv comma q dv, and then outside I have a du. Is this okay? I've skipped a step here. Yeah. Okay, I've used the fundamental theorem of calculus on this term inside, and I've made a change of variable. Okay. Is this all right?
Yes.
Yes.
So I have a t outside. Okay. Now look at this first term. Del phi del t at 0 comma q is what? It's just the derivative of the integral curve phi t of q, right? So the derivative of this at t equal to 0 is just x at q, right? So this term here is just x at q. So that's constant, independent of u. So when I integrate from 0 to 1, I'll just get x of q, right? So this becomes q plus, oh yeah, this phi of 0 comma q, this is just the identity. So this is q, okay? So I get q plus t times x of q, plus now I have this t times a t inside here, right? So I'll get a t squared, and then what remains is some function of q and t. So I'm calling that r sub t of q, where r sub t of q is the function for a fixed t. This is the function of q. So I have this u inside here, and I get a double integral 0 to 1, integral 0 to 1, u times del squared phi del t squared tuv comma q dv du. All right. Is this okay? So this is a smooth function of q. Okay. Yes.
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 So now I take, so this is my phi t of q. So I now take the derivative with respect to the q variable on both sides, okay? So then this becomes on the left-hand side d phi t at the point q. And so the derivative of the first term, this is the identity. Derivative of the identity is just the identity. So I get identity plus t times the derivative of x at q plus t squared times the derivative of rt at the point q. All right? Yes? So I have this d phi t at q is equal to identity plus t dx at q plus t squared drt at q. All right? Okay. Now I use the fact that the Lie bracket between x and y at p, this is equal to the Lie derivative Lxy at p. Okay. So what is the Lie derivative? This is a limit as t tends to 0 of d phi minus t at the point phi t of p applied to the vector y at phi t of p minus the vector y at p divided by t, right? This is the Lie derivative. Yes?
Yes.
Okay.
Yes, sir.
So now I use the formula for d phi minus t, right? I use this formula. So it's going to be identity minus t times dx at the point phi t of q of p plus t squared times this drt, right? So when I use this formula here, I substitute this for d phi minus t at phi t of p. So first I'll get the identity term. So that will just give me y at phi t of p. And then I have this minus yp. So I'll get y at phi tp minus y at p divided by t. And then I'll have a minus t dx at q, right? So that will cancel with the t here. The t and the t will cancel. So I'll get a minus dx at phi t of p applied to y at phi t of p, right? And then I'll have a t squared term. So the t squared will cancel with the t below here to give me a t. All right, so I'll get t times d of r minus t at the point phi t of p applied to y at phi t of p. Is this okay?
Yes.
So now, as t tends to 0, this last term goes to 0, right? Because I have a t factor here. Okay, and this this term here is smooth in t and p. So this is bounded. All right, so this is bounded and t goes to 0. So this term goes to 0. Okay, so this vanishes. So what remains? Well, this term here, y at phi t of p minus y at p divided by t. This phi t at p, this is the integral curve of x. So it's the tangent vector to this curve at p is just x at p. So this is the derivative of y in the direction of x, right? So this will be dy at p applied to x of p. This first term, yes, minus this second term when t tends to 0, phi t of p just converges to p, and y at phi t of p converges to y at p. So this second term converges to minus dxp at y of p. Okay. All right, so the bracket is equal to this dyp xp minus dxp yp. But note that the bracket belongs to TPM, right? The bracket of two vector fields tangent to M is also tangent to M, right? By definition, the bracket is a vector field on M, so it's tangent to M. So this vector here is equal to its tangential component, right? So I can take the tangential component of the whole thing here. And then when I apply tangential component to the first term, what do I get? This by definition will be nabla xy at p minus this by definition will be nabla yx at p. Is this clear?
Yes, sir.
Sir,
Right? Yes.
so why is that last term that dr minus t, that thing is bounded? Why is that part bounded?
Because this r as a function of T and P, or T and Q here, this is smooth in T and Q, right?
Okay.
Is that clear? Look, you have a
Yes.
T here and a Q here, and
Mhm.
this phi is a smooth function
Smooth function.
of both variables. So this is smooth in T and Q, so its derivatives are also continuous, right?
Yes.
So they're bounded locally.
Okay.
Is that all right? Yeah.
Yes.
Okay. So let's. Okay, so this proves the symmetry. Is it clear?
Yes.
Yes. Okay. And for the metric compatibility, we just use the fact that this inner product that we have, this is the Euclidean inner product, right? So so the Euclidean inner product, of two vectors, suppose they're vectors. So if I look at two vector fields along a curve, so then they become, summation. I can write them as summation AI of t, summation bj of t, ej, right? And so this becomes what? This inner product is just sum over I AI of t bi of t, right? So if I differentiate this ddt, then I'll get summation AI prime t bit plus summation AIT bi prime t, and the first term is equal to the inner product of ddt of summation AI EI with summation bi EI, plus the second term is inner product of summation AI EI with ddt of summation bi EI. Is this clear?
Yes.
Yes. So if I am taking two vector fields y and z, what is x of y, z? X applied to this at P. This is basically ddt of at t equal to 0 of the inner product between y at the point. I have to differentiate this function in the direction of x. So that means differentiate along an integral curve of x. So this will be y at phi t of P, inner product with z at phi t of P, right? And so by the calculation that I've done just above, this is equal to inner product of ddt at t equal to 0 y phi t P with z at P. When I put t equal to 0, I get z at P here, plus inner product y at P ddt at t equal to 0 z at phi t of P, right? And so this becomes inner product of dyp applied to the vector xp, right? Because I'm differentiating y along a a curve which is tangent to x at P. And the second term becomes inner product of YP with DZP of XP. Right? Is this okay? And now you use the fact that Z and Y, these are tangent to M, right? So this inner product is the same as the inner product with just the tangential components, right? Yes?
Yes.
Yes, sir.
Okay, so this is because ZP, YP belong to TPM. And by definition, what are these tangential components? This is nabla XY at P. And the other term is inner product YP with nabla XZ at P. Is this clear?
Yes.
Okay. So what have we seen? We've seen that to summarize, any submanifold of Rn becomes a Riemannian manifold with the induced metric. Curves, C2 curves of shortest length by the calculus of variations, the Euler-Lagrange equation for the length functional. They are minimizers of the length functional. The Euler-Lagrange equation is the geodesic equation, that is gamma double prime tangential component is 0. That we write as, that leads us to the idea of covariant derivative of a vector field along a curve. And that's just the usual derivative, and then you take the tangential component. And so then the geodesic equation becomes the covariant derivative of gamma prime is 0. Okay, this is the geodesic equation. And so then we define the notion of connection, and we are able to define a connection on any submanifold of Rn called the induced connection. Okay, so in addition to the usual 3 axioms for a connection, it satisfies these other 2 properties, symmetry and metric compatibility. Okay. All right, fine. So now we can come. So all this was motivation for the general case of an abstract manifold, which is not necessarily embedded in Rn. Okay. In the general situation, we would like also to have a geodesic equation and covariant derivative. We would like to define covariant derivatives of vector fields. Okay. Now on a general manifold, like we showed the existence of a Riemannian metric by using partitions of unity, you can also show the existence of a connection. Okay, using partitions of unity, you can define a connection on any Riemannian manifold. Okay, because locally you can identify the manifold with Rn, and in Rn, your vector fields then become maps which take values in Rn. So you can just take their usual derivative, for example. That will give you a connection locally. And then you multiply with bump functions, which are with your partition of unity, and you sum up these local connections to get a global connection. All right, so it's easy to verify the sum of connections will again be a connection. Okay. Does this make sense?
Yes.
Okay, so you can show that on any manifold there exists a connection. So that's not difficult. The point is you want a connection which is well adapted to the Riemannian metric, to the Riemannian structure of the manifold. And so here we have the following theorem, which describes what is called the Levi-Civita connection of a Riemannian manifold. So suppose Mg is a Riemannian manifold, then the theorem says there exists a unique connection nabla on M, which in addition to the usual actions, it satisfies symmetry and metric compatibility. Okay, so that means that nabla xy minus nabla yx is equal to bracket xy. And now we have a Riemannian manifold, so the inner product of two vector fields makes sense. So then x of inner product yz is equal to inner product nabla xy with z plus inner product y with nabla xz. Okay. So this second condition is saying that, you know, your connection behaves well with respect to the Riemannian metric, right? The Riemannian metric satisfies the product rule, the Leibniz rule, with respect to this connection, and it satisfies symmetry. Then there is a unique such connection. Okay, such a connection exists and it is unique. So this is what this theorem says. This theorem is sometimes called the fundamental theorem of Riemannian geometry. Okay, so this connection is called the Levi-Civita or Riemannian connection of Mg. Okay, so I'm not going to prove this, I'm just stating it. Is this all right? The statement is okay?
Yes, sir.
Yes.
Yeah. So this may seem abstract, but we know how to get the Levi-Civita connection for a submanifold of Rn, right? You just take the usual derivative of your vector fields as maps into the ambient space, R capital N, and then take the tangential component, right? That has to give you the Levi-Civita connection, because it, as we've just shown, it gives you a connection which satisfies symmetry and metric compatibility, right? So therefore, by uniqueness, it must be the Levi-Civita connection. Is it clear?
Yes, sir.
Okay. Okay, good. So this Levi-Civita connection is the fundamental object of Riemannian geometry for us. Okay, using this, now we can proceed. So first, let's talk a bit more about connections. So first of all, so recall that connection satisfies these three axioms. The third axiom, this Leibniz rule, this actually, whenever you see a Leibniz rule for a linear operator acting on functions or tensors or something, this Leibniz rule actually will tell you that this operator is a local operator. In other words, nabla x of y only depends on y in a neighborhood of a point P. Okay, so it only depends on the germ of y at P, and it only depends on the germ of x at P also. Okay, so so that's what I mean when I write here localizing the connection. Okay, so suppose yz are two vector fields on M, and x1, x2 are two vector fields on M, such that y is equal to z and x1 is equal to x2 on a neighborhood U of P. Okay, then what I want to say is that nabla x1 of y is equal to nabla x2 of z at P. All right. So basically, I'm looking at nabla x1 of y, and then I want to say that if I change y to another vector field z, which is equal to y in a neighborhood of P, and if I change x1 to x2, which is equal to x1 in a neighborhood of P, then my connection does not change at P. Is it clear? Okay, that's what I want to show. All right. And that will let me localize the connection. All right. So you choose a bump function phi with compact support contained in this neighborhood U of P, where these functions are, where these vector fields are equal, such that phi is equal to 1 at P. Okay, so phi is 1 at P and it vanishes outside U. So if I look at the vector field phi times y minus z, this is going to be identically 0. Why? Because if I'm inside the neighborhood U, then by hypothesis y is equal to z. So this is 0 inside U. And if I'm outside U, then phi is 0. So this is also 0, right? Similarly, phi times x1 minus x2, this is also identically 0. Is this clear?
Yes, sir.
Okay, now we know that the connection, it is R linear in the second variable, right? It is R linear in the second variable. So therefore, nabla x1 of phi times y minus z, this is going to be 0 because phi times y minus z is identically 0 on the whole manifold, right? Yes.
Yes, sir.
Yes.
Okay, and it's R linear. So linear map applied to the 0 vector is 0. So now I use the Leibniz rule. Okay, so this is going to be phi p into nabla x1 of y minus z. So that's nabla x1 y minus nabla x1 z at p, right? Plus x1 applied to phi at p into yp minus zp, right? So now look at the first term. Here I've chosen phi so that phi p is 1. So this becomes 1 times nabla x1 y minus nabla x1 z at p. And the second term vanishes because yp is equal to zp, right? So this becomes simply nabla x1 y minus nabla x1 z at p. And this is equal to 0. So this tells me that nabla x1 y at p is equal to nabla x1 z at p. Okay. So this gives me the first part that if I change the vector field y to a vector field z such that they're both equal in a neighborhood of P, then nabla does not change, right? Okay.
Yes.
Similarly, to show that nabla does not change when I go from x1 to x2, I look at nabla sub phi times x1 minus x2 applied to y, right? Now, phi times x1 minus x2, this is identically 0 on the manifold. And nabla is linear in the first variable as well. So this is also 0, okay? And this by linearity with respect to C infinity m, this becomes simply phi of p into nabla x1 minus x2 of y. Again, by linearity in the first variable, this becomes nabla x1 y minus nabla x2 y. So this is 0 and phi p is 1. So that tells me that nabla x1 y minus nabla x2 y at p is 0. So therefore, nabla x1 y is nabla x2 y at p. Okay. So therefore, nabla does not change if I change x1 to x2 such that they are equal in a neighborhood of p. Okay. So now I can localize my connection as follows. If I take any open set U in N, we can define a connection on U just on the open set by saying whenever xy are vector fields on U, then nabla xy at P, this is defined to be what? Well, if I take a point P in U and xy are vector fields on U, then by multiplying by bump functions, I can extend xy to, I can get extensions, I can get global vector fields, x tilde, y tilde, which are vector fields on all of M, such that x tilde is equal to x and y tilde is equal to y in a neighborhood of P, right? This I can do by multiplying by a bump function, which is 1 in a neighborhood of P, right? Then I will get global vector fields, x tilde, y tilde, right? Why do I need to do this? Because a priori, my connection is only defined on global vector fields, right? It's defined on chi-m cross chi-m to chi-m, okay? So I need to get global vector fields x tilde, y tilde. I just insist they are equal to x and y in a neighborhood of P. And then I can apply nabla to x tilde, y tilde and evaluate it at P. All right. Now, because of what we just did above, this is independent of the choice of x tilde and y tilde. Is this clear?
Yes, sir.
Okay. And you can check this satisfies the axioms for a connection on U. Okay. So therefore, any connection gives you an induced connection on any open subset of M. Okay, so we are able to localize the connection. Is it clear?
Yes, sir.
Now, why do we want to localize the connection? Because we want to describe it using charts, right? So now we can localize our connection to a chart, and we take a chart U comma phi, where phi is given by functions x1 to xn. So then del del xi's are vector fields on U, right? And I can look at, therefore, my connection applied to del del xi and del del xj, right? Because I've localized it, so it makes sense applied to these local vector fields. And applied to these vector fields, it's going to be again a vector field on U, and any vector field on U is a linear combination of the del del xk's with coefficients which are smooth functions. So these will depend on I, j, and k, right? So these are written as gamma sub ij super k. All right. So these are smooth functions on U. These are called the Christoffel symbols of the connection. Okay. These are called the Christoffel symbols of the connection. So the point is, the connection is completely determined by these Christoffel symbols. Okay. See, these Christoffel symbols, they determine the connection applied to the basis vectors del del xi, del del xj. Then using linearity and the Leibniz rule, once you know nabla del del xi, del del xj, you can compute nabla xy for any pair of vector fields xy on U. Okay. So let's do that computation. So suppose x is x and y are vector fields on U. So x is summation ai del del xi, y is summation bj del del xj. Okay. So let's write xk to be the vector field del del xk. Okay. So let's compute now nabla xy. So this is nabla sub summation ai xi, right, applied to y. So by C infinity and, well, C infinity U linearity in the first variable, this becomes summation over I, ai nabla xi of y. Now y is what? Summation over j, bj xj. And now I use linearity and the Leibniz rule, right? So this is going to become inside bj nabla xi xj plus xi applied to bj. So what is xi? Xi is del del xi. So del del xi applied to bj is just del bj del xi into xj. Is this clear?
Yes, sir.
Okay. And now what is nabla xi xj? Xi is del del xi and xj is del del xj. So this is just the sum over k gamma ij k xk, right? By definition of the gamma ij k's. Okay. So I get this. So now I've got a linear combination of xk's and xj's, which are the basis vectors. And so I just rearrange terms and write these. So I write this as a sum over k now. I interchange the summation. I take the sum over k outside here. And then inside I get a sum over ij, ai, bj, gamma ij, k. Right? This becomes my coefficient of xk. Plus this second term here gives, I interchange the sum over j and I. So the sum over j I take outside. I get a sum over j. And then inside I get a sum over I, ai, del bj, del xi. The whole thing into xj. All right. And finally, this, I want to put these two sums together. So this j in the second sum, I rename it to k. And so then this becomes a sum of xk's times some coefficients. I put them together and I get this formula. Okay. Finally, I get that nabla xy is sum over k inside sum over I, ai, del bk, del xi plus sum over ij, ai, bj, gamma ij, k. The whole thing into del del xk. Is this clear?
Yes, sir.
So what does this tell me? This tells me that my connection nabla is determined by the gamma ijk's, right? If I know the gamma ijk's, then I can compute nabla xy for any vector fields xy. Yes?
Yes.
Is that clear? And it also follows from this formula that if I look at the dependence on x, so x was summation ai del del xi. ai's are the coefficients of x. So you know that nabla is linear in x, C infinity M linear. So here what you get is this expression, the coefficients are linear in the ai's, right? As expected. And not just linear, but they don't depend on any derivatives of the ai's. Okay. Yeah. So we've got this expression for nabla xy. And you can see that with respect to the ai's, which are the coefficients of x, you don't have any derivatives of the ai's, right? You have derivatives of the bj's, which are the coefficients of y. That makes sense because you're differentiating y with respect to x when you're taking nabla xy, right? So you expect to find derivatives, first order derivatives of the coefficients of y appearing, but there are no derivatives of x appearing. So what that means is that nabla xy, this only depends on the value that the value of nabla xy at p only depends on the value of x at p, right? I mean, if you have two vector fields x1, x2, which are equal at p, then nabla x1 y at p will be equal to nabla x2 y at p, right? Because the coefficients of x1 and x2 will be equal at p. And this only depends on the coefficients, the values of the coefficients at p. Is this clear?
Yes, sir.
Okay. So that means with respect to the first variable, we can, in a sense, localize the connection even further. That is, if y is a vector field on an open subset U of M, and P is a point of U, and V is just a tangent vector at P, sorry, then we can define the covariant derivative of y in the direction of the vector V. Okay, nabla sub V of y, this is defined to be nabla sub x of y at P, where X is any vector field on U such that X at P is equal to V. Okay. This is well defined because of what we just said here, right? The covariant derivative only depends on the coefficients, the values of the coefficients of the first vector field at P. All right. So it only depends on the value of the vector field X at P. Okay. So this is well defined. Is this okay?
Yes, sir.
So, we've got, we've sort of gone backwards from the way that we did for submanifolds of Rn, right? For submanifolds of Rn, we started with this nabla sub V of Y, that is the covariant derivative of a vector field with respect to a tangent vector. And then we defined the connection covariant derivative of a vector field with respect to another vector field. Here we've gone backwards. We're starting with the information for vector fields, covariant derivative of a vector field Y with respect to a vector field X. Then we're seeing that from that global object, we are able to localize it to an open set, first of all, any open set. And then we can localize in the first variable even further. We can localize to a tangent vector at a point. Is it clear?
Yes.
Any questions?
So on the second variable, we can localize it to an open set, and on the first variable, we can localize it to a point. That's what you're saying.
Exactly. See, that makes sense, right? Because if you look at the axioms for a connection, so this has nothing to do with the symmetry or metric compatibility. This localization is just, this is following from the basic axioms 1, 2, and 3 of a connection. So essentially, the fact that in the second variable, we can localize to any open set, that comes from the Leibniz rule, okay? The Leibniz rule allows us to localize to the second variable to any open set. In other words, in the second variable, the connection only depends on the germ of Y. Is it clear?
Yes.
Okay, so the Leibniz rule will tell you that the connection only depends on the germ of Y. And the fact that we are able to localize to a point in the first variable, that follows from the first axiom that the key point is that the connection is C infinity M linear in the first variable. That allows us to localize to a point. Okay, so any so maybe I should make a general remark here. Which is the following. So see, we have a connection, nabla. This goes from chi-m cross chi-m to chi-m. Okay. Now, if I take a form omega, let's say a K form, okay, this I can this will define for me a map from chi-m cross chi-m k times to C infinity m, right? It's just the obvious thing that omega applied to k vector fields x1 to xk, this at a point P, this is defined to be omega at P applied to x1 at P up to xk at P, right? Okay.
Yes.
Okay. Now, similarly, more so omega is a section of the kth wedge of the cotangent bundle, and this I can also, this is a subspace of the sections of the kth tensor power of the cotangent bundle, right?
Yes.
The k forms just correspond to the k tensors which are alternating, right? Okay. So more generally, if I have T is a section of the kth tensor power, so this is called a k tensor. Okay, this is called a k tensor. Okay. So T is a map from M to T star M tensor K. P in M maps to TP, T sub P, which is oh, my notation is bad here. Sorry, I shouldn't use T because so let me use S. Fine. Let me use S. S sub P. This is an element of TP star M tensor K. What that means is SP is a K multilinear function, right? From TPM cross TPM to R, right? This is K times product. This is multilinear. Is this clear?
Yes, sir.
This is called a K tensor. Now, any K tensor S gives me K gives me okay, so a K multilinear map which I'll also write as S from chi-m cross chi-m to C infinity m. This is k times, which is defined in the natural way that S of k vector fields x1 up to xk. So this is supposed to be a function in C infinity m. This at a point P is defined to be S at P applied to the vectors x1p up to xkp, right?
So in fact, this S will be C infinity linear.
Exactly. So that's what I was going to say. So if I multiply the xi's by functions fi's, then because at each point sp is a multilinear function on the tangent space, the fi's will come out, right? So this is in fact C infinity m linear. So this is C infinity m k multilinear. Is this clear? Yeah.
Yes.
Yes.
Now, here is the point. The point is that you can go backwards in this correspondence. That is, any C infinity m k multilinear map S from chi-m cross chi-m cross chi-m to C infinity m, because it is C infinity m linear, you can look, first of all, you can localize this in all the variables. You can localize to open sets, and further you can in fact localize to points. You can localize to a point in this. Okay, so so in other words, a C infinity m k multilinear map from chi-m cross chi-m cross chi-m to C infinity m, this will give you back a k tensor, which is a section of the kth tensor power of T star m. Okay. So in fact, there is a one-to-one correspondence between these. Okay. And the key point is the C infinity m multilinearity. Okay, this allows to localize at a point. This allows to localize at a point. Okay, so do you want me to explain how this works, or should I carry on?
Yeah, this is fine.
This is a standard thing. Okay. So the point is, for a connection, you have something similar, except it doesn't take values in C infinity m, it takes values in chi-m again. But the point is that this is C infinity m linear in this variable, in the first variable. This allows us to localize to a point in the first variable. Okay. It is not C infinity m linear in the second variable, which is why we can't localize to a point in the first variable, in the second variable. All right. Is this okay?
Yes, sir.
Any questions? Orkojit?
Yes. Fine.
It's fine. Yeah. Okay, good. So we have on any Riemannian manifold, a unique Levi-Civita or Riemannian connection, and we can localize it. And after localizing, it's determined by the Christoffel symbols. Okay, now I'm going backwards. So backwards to what we did for submanifolds of Rn. So now I want to use the connection nabla to define the notion of covariant differentiation of vector fields along curves. Okay, so suppose gamma is a smooth curve in my manifold defined on an interval I in R. So as before, a vector field along gamma is a smooth map V from I into Tm such that Vt belongs to T sub gamma Tm for all T and I. Okay. So for example, you can take V to be gamma prime, right? So gamma prime is a vector field along gamma, right? At each point, gamma prime T belongs to T gamma Tm, right? Okay, so gamma prime is you always have this vector field along gamma. Another example is you take a global vector field X on M and you restrict it to the curve, right? So you look at the map X composed with gamma. So that goes from the interval I into Tn. Is this clear?
Yes.
Okay. Now we have the following definition proposition. Okay. So let chi of gamma be the space of vector fields along gamma. Then there exists a unique linear map. So when I say linear, I just mean odd linear with respect to scalars. Capital D sub dt from chi gamma to chi gamma. V goes to capital dV dt, which is called the covariant derivative along gamma. Okay, so this is an operator which is covariant derivative along a curve. Okay, it acts on vector fields along curves. It allows you to differentiate a vector field along a curve. Okay, which satisfies the following two rules. One is the Leibniz rule. So capital D sub dt of f times v is f dv dt plus df dt into v, where f here is a function on the interval I, right? So if I have a vector field along gamma, then I can multiply it by a real valued function on the interval I, right? Okay. So what I require is that for all vector fields v along gamma and functions f on I have this Leibniz rule. Okay. And the main property which I need, which makes my covariant derivative unique, is the compatibility with the connection nabla, that dv dt, if v is of the form x composed with gamma, that means the restriction of a global vector field to my curve, then this is equal to just nabla sub gamma prime t of x. All right. So remember, the applied to vector fields, I can localize the connection to a tangent vector. So this nabla sub gamma prime t of x, this makes sense, right? Okay. Okay, so this is the relation between the covariant derivative along the curve and the covariant derivative nabla of vector fields. Whenever I restrict a vector field to the curve, then the covariant derivative along the curve should be equal to just the connection applied to the vector field in the direction of gamma prime. Is this clear?
Yes, sir.
Okay. So I don't know if I've done the proof of this. I don't think so. But I just want to say that as before, the Leibniz rule allows you to localize the covariant derivative along a curve again. So one implies that capital D sub dt is a local operator. That means if V and W are two vector fields along gamma, which are equal in some interval around a point T naught in I, then dv dt and dw dt at t naught will be equal to 0. Will be equal. They will both be equal. So how do you do that? We do the same kind of thing we did when we were localizing nabla. You choose a function f with compact support in this interval where the two vector fields are equal. Then as before, f times the difference v minus w. This is identically 0 on the whole interval. So therefore, by linearity of the covariant derivative, d sub dt applied to the 0 function, to the 0 vector field is 0. So this applied to f times v minus w at t naught is 0. Now you use the Leibniz rule. This is going to be f of t into dv dt minus dw dt at t naught. We choose f of t naught. We choose f so that f of t naught is 1, like we were doing earlier. Okay. And then you get plus df dt at t naught into vt naught minus wt naught. So this second term vanishes because v is equal to w on a neighborhood of t naught. Okay. And so so this becomes just dv dt at t naught minus dw dt at t naught. So therefore dv dt at t naught is equal to dw dt at t naught if v is equal to w on a neighborhood of t naught. Okay. So just like we did for nabla, similarly we can localize d sub dt, the covariant derivative along a curve. Okay. So once you can localize it, then again we can look at it in a chart basically. So now I want to, again, we describe how to localize the connection, the covariant derivative. So if J is a open subinterval of my interval I, then we can define d sub dt from vector fields along gamma restricted to J to vector fields along gamma restricted to J by saying that dv dt at t naught, this is defined to be dv tilde dt at t naught when t naught is in J, and v is a vector field along gamma restricted to J where v tilde is a vector field along all of gamma such that v tilde is equal to v in a neighborhood of t naught. Right? So by what we've just done above, this is well defined, independent of the choice of v tilde, right? Is this okay?
Yes, sir.
Okay, and so then it's easy to see that the covariant derivative along vector, the curve restricted to J, this will also satisfy the axioms 1 and 2. So actually, yeah, so it's not hard to see this. So I'm not going to, I've done the proof of 2 here, but I'll just skip that. It's not very difficult. So what I want to do is compute an expression for the covariant derivative d sub dt in local coordinates. Okay. So you let u phi be a chart. Phi is x1 to xn. You let j be an interval in I such that gamma of j is contained in the chart u. So then I can compose my chart phi with gamma. So this gives me a curve in Rn, and I let the coordinates of that curve in Rn be x1t up to xnt, t in j. So now let V be a vector field along gamma restricted to j. So then Vt I can write as summation Vi of t del del xi at gamma t, right? For some functions Vi. So then I use the properties of the covariant derivative, the Leibniz rule first of all. So linearity and the Leibniz rule. So dv dt, this is by linearity, summation over I, well, by the Leibniz rule, Vi into d dt of del del xi plus Vi prime into del del xi, right? This is the Leibniz rule for the covariant derivative along gamma, right? Now, del del xi, this is a vector field along gamma, which is the restriction of a global vector field on U, right? Yeah, del del xi is a vector field on U, and I'm restricting it to a part of gamma, right? So this, by the compatibility with nabla, capital D dt of del del xi, this is going to be nabla sub gamma prime t applied to del del xi. And note that gamma prime is summation over j xj prime del del xj, right? Okay. So, so this becomes nabla sub sum over j xj prime del del xj applied to del del xi plus summation vi prime del del xi. Now I use linearity of the connection in C infinity and linearity of the connection in the first variable. So this sum over j will come outside. So I'll get a sum over ij. And then I'll get this xj prime will come out. So I'll get vi xj prime. And then I'll get nabla sub del del xj del del xi, right? So that will be a sum over a k gamma jik del del xk, where these are the Christoffel symbols, right? And then I have plus sum over I vi prime del del xi. So finally, what do I get? I get a sum over k. I write everything as a combination, linear combination of del del xk's. So here I'll take the sum over k outside, and then I'll get inside a sum over ij xi prime vj gamma ij k, right? Plus from here I'll get a vk prime, the whole thing into del del xk. Is this clear?
Yes.
Okay. So recall now, xi's, these are the components of the curve in coordinates, and the vj's are the coefficients of the vector field, right? So notice what we're getting here. We're getting the derivatives of the components of v, okay? So this would be like the usual derivative. And then you have this extra term, which is linear in v, and which involves the Christoffel symbols, all right? So the covariant derivative, it differs from the usual derivative just by this term which involves the Christoffel symbols. So if the Christoffel symbols vanish, then the covariant derivative is just the usual derivative where you differentiate just the components with respect to the basis del del xi. Okay, does this make sense?
Yes.
Okay. Okay. So to finish, we make one important definition that a vector field V along a curve is parallel along gamma if its covariant derivative is identically zero. dv dt is identically zero. Okay. So before going further, I should just say, see, we've stated that there exists a unique covariant derivative along any curve, right? Given the connection nabla on the manifold M, there exists a unique covariant derivative along a curve. This covariant derivative along a curve, we know what it is for a submanifold of Rn, right? For a submanifold of Rn, a vector field along the curve, you can think of as a map into the ambient space Rn, taking values in vectors in Rn, and then you just take its usual derivative, little dv dt, and then take the tangential component, right? That's what we did for a submanifold of Rn. Yes?
Yes.
Okay, this was our covariant derivative along a curve. So for a submanifold of Rn, the covariant derivative along a curve is very explicit. It's just the tangential component of the usual derivative, where you think of V as taking values in R capital N. All right? Okay. Fine. All right. So, so to finish, yeah, let's just talk a bit about parallel vector fields. So a vector field V is parallel if its covariant derivative along gamma is 0. So since the ddt is a linear operator, the set of parallel vector fields will be a vector space. It's the kernel of ddt, right? So let P of gamma be the vector space of parallel vector fields along gamma, okay? Then, what is the dimension of this space of parallel vector fields? How can we describe it? So note that V is parallel if and only if in any chart its covariant derivative is 0. So in the chart, the covariant derivative is given by this linear combination of the del del x case. So these coefficients have to be 0, right? Okay. So that gives us a system of n differential equations, linear differential equations in the V case, right? Vk prime plus sum over ij xi prime gamma ij k vj is equal to 0, right? Okay. So this is a system of linear ODEs in Rn with smooth coefficients, right? This is linear in the V case. Yes.
Yes.
So what is the point? For linear ODEs in Rn, we know that solutions are actually defined for all time. Like as long as the coefficients are defined, the solutions exist as long as the coefficients are defined, right? This is something special to linear ODEs, right? Okay.
Yes.
Yes. Okay. Sorry, 1 second. Someone is ringing the bell. I'll just come back. Sorry. Okay. All right. So, because this is a system of linear ODEs, right? In the V case, the solutions are defined on the whole of the interval J. And so, therefore, if given any initial condition, an initial vector at a point on the curve, you will get a unique parallel vector field, right? On the interval J, right? And then this we did for a part of the curve which was contained in a chart. But for the whole curve, what we can do is we can cover it by finitely many charts. And then we can, on each chart, we know we have a parallel vector field, a solution to this linear ODE. And then we can glue together the solutions to get a solution on the whole interval. Does this make sense?
Yes.
Yes.
Okay, so I'm not going to go into details in that. You can glue together the solutions in charts. And so what we get is that finally, for any point T naught in I, and for any vector V in T gamma T naught of M, there exists a unique parallel vector field V along gamma, whose value at T naught is equal to the given vector V. Okay. So, so this is M, say, and I'm taking a vector V at a point gamma T naught. Okay. Then there exists a unique vector field, parallel vector field, capital V, so that its value at T naught is equal to little v. Okay. Okay. All right, so let's stop with this picture since we have less than a minute, and we'll continue next week. Okay.
I actually had one question, sir, but I guess.
So then we can just continue for 5 minutes if you want. We
Yeah,
just
yeah.
start a session for 5 minutes. Okay, fine. Let's just do one more session for 5 minutes. Okay.